Watch an LLM agent navigate a multi-hop search task, and you'll often see it get stuck in a reasoning loop, unable to correct its behavior. Language models that learn from experience usually write their lessons down as text. But when an agent reads a textual rule warning it not to repeat a specific error, the result often lags behind a system with no rules at all. This chart compares web search reasoning accuracy across agent setups. The first bar shows our baseline, a standard React multi-loop agent successfully answering the prompt 31.2% of the time. When researchers inject learned lessons back into the prompt as text, accuracy drops to 20.5%. Researchers identify this exact failure as the advisory gap. The core issue is timing. A text prompt cannot bind itself to a specific decision point. The phrase "verify before finalizing" has no programmatic hook into the exact turn where the agent decides to stop searching. Text also lacks a mechanism for enforcement. It requests a behavior, but relies entirely on the LLM to execute it. The system receives no feedback on whether the requested lesson was actually applied. HASP solves this by upgrading the representation of a skill. Instead of descriptive text, a skill becomes a program function, executable code. By making skills executable at inference time, accuracy jumps to 51%, doubling the performance of prompt-injected rules. Treating past failures as passive reading assignments guarantees inconsistent execution. Reliable agents require executable guardrails that force compliance. In a standard React policy loop, the architecture is simple. The base LLM proposes an action, and that raw action directly hits the execution environment. HASP breaks that direct connection. It inserts a control layer strictly between the policy's proposal and the environment itself. The active unit inside this control layer is the program function, a typed Python object governed by a strict two-method contract. Inside the harness node, an action hits a logic gate labeled should activate. This gate directly solves the timing problem. It intercepts the model at the exact fraction of a second a failure is proposed. If the predicate fires, it triggers the second method, intervene. This executes the repair via external code, rather than relying on internal generation. Interventions take exactly two forms. The first is modify action, which directly rewrites the proposed executable decision before it is allowed to run. The second is inject context. This leaves the original action untouched, but adds corrective reasoning hints directly into the data stream for the next turn. The harness separates action proposal from action execution. The LLM guesses what to do. The harness decides if that guess goes through unmodified, gets rewritten, or gets augmented. We can see this architecture work on a two-hop benchmark problem, identifying the corporate acquirer of a highly specific UK record label. The baseline React agent fails immediately. It proposes an over-constrained 16-word conjunctive search query stuffed with irrelevant distractors. Because of that bloated query, the baseline agent thrashes helplessly, pulling up massive corporate entities like Sony instead of the target data. It then pivots to universal, burning through its token limit without ever verifying the specific UK label it was asked to find. Now we reset the scenario using the HASP-enabled agent. The LLM proposes the exact same flawed 16-word action, but this time a program function named retrieval.failure intercepts the action. Its activation predicate fires because it detects the string length constraint has been violated. The harness executes a modify action command. It programmatically compresses the 16-word query down to an effective 9 words. On the very next step, the agent correctly identifies CBS buying Oreo records. The model possessed the knowledge to solve the prompt, but it lacked the execution. Rewriting the query with mid-loop code succeeds where asking the LLM to edit its text fails. Every time a program function intercepts an action, the loop structurally emits a highly valuable byproduct, a refined piece of data. This structured record is an automated log containing 4 precise data points: the triggering state, original action, corrected action, and outcome. Placed side by side, it captures exactly what the policy would have done versus what the harness did instead. This turns runtime inference into a synthetic data generation engine. The agent produces its own training pairs, completely eliminating the need for human labeling. These records feed a post-training recipe called PF-guided rejection sampling. The system retains only trajectories that score highly on task success and intervention quality. Each record is scored using 4 weighted signals: the final outcome, which carries 50% of the weight, followed by the correctness of the repair, the timing of the trigger, and the mode of intervention. While on-policy distillation works well on fixed skills, it becomes unstable if the external skill library and the visited states shift at the same time. Rejection sampling stays robust even while the library of skills evolves. Using this supervision, HASP drives average task performance up to 60.3%. The HASP harness operates as an automated supervision pipeline, training the agent's internal weights directly on its own corrected mistakes. There is a specific risk in allowing skill libraries to self-evolve. Algorithms auto-generating code from failures quickly pollute their retrieval space with bad data. This line graph maps web search accuracy under unfiltered evolution. Performance peaks at 60.3% and then abruptly collapses to 36.3%. Without strict checks, noisy and overly specific program functions flood the library, triggering false interventions that sabotage the agent. HASP prevents this using a double gate filter. Every newly generated program function must pass both gates before admission. Gate 1 is a mechanical check. It runs a mock execution to validate syntax, verify interface signatures, and guarantee legal return types. Gate 2 is a semantic check. A stronger teacher model reviews the code to confirm it captures a reusable pattern, fires on appropriate triggers, and proposes a genuinely useful repair. In agent ecosystems, the engineering bottleneck is no longer how fast a system accumulates skills. It is the strict, programmatic governance of what gets admitted. Once an agent completes post-training on its own structured records, do the external program functions become obsolete? The data shows a split reality. Behavior-correcting skills, like rules preventing overlong queries, go silent on 100% of previously triggered cases. The model's weights fully internalize the rule. The LLM also internalizes a broader behavioral shift. It executes significantly more search and read actions and attempts far fewer zero-search final answers. However, input-dependent skills, like injecting complex decomposition hints for multi-hop questions, rarely internalize. They continue to fire actively turn after turn. Only 8 to 38% of the accuracy gain is actually absorbed into the model's weights. The remaining 62 to 92% requires the external program functions to remain active. The harness is a permanent requirement, not a temporary training wheel. Program functions do not help models discover genuinely new mathematical strategies through reinforcement learning. They exist solely to stabilize the strategies the model already technically understands. Reinforcement learning remains necessary to discover the unknown, but executable code guardrails are the only way to guarantee an agent actually executes what it already knows.